Let's talk about friction. So the situation we have here is I'm going to be pulling this string with a force sensor. I'm going to pull it to the right, and I'm pulling this wood block that has some mass on top of it. We're going to treat the wood block and the masses as one object that we can change the mass of by taking some of these off or placing more on. So let's look at what happens first. So first, I pull on the mass, and what do I notice happening? Well, nothing happens. So I pull on the mass, but the block doesn't move. Real quickly, let's draw a free body diagram to explain why this happens. So, on this mass, there's the force of gravity acting down because it has mass and it's under the influence of Earth's gravity. Because it's not moving up or down, there must be an up force to balance that out. That's the table pushing back up on the mass. I am pulling to the right with a tension, and if it is not moving, it's what we call equilibrium. So if I have a right force, I must have an equal left force, and that left force that's balancing out the tension is friction. So this is my free body diagram. I've got four forces. I know that up equals down, left equals right because of equilibrium. And I know this object is not moving, and I know it's because of friction. Now this is a specific type of friction called static friction. Static means not moving. So static friction occurs when an object is being kept from sliding and it is not moving. Let's keep going. So next I pull it, and it actually does move. When it does move, my free body diagram is still the same. I've got normal force, gravity, tension, and there still is friction here because now, even though I'm moving, I'm still sliding against the table. If I'm actually sliding and there's actually that sliding motion, that is called kinetic friction. And kinetic friction happens when sliding between two surfaces occurs. We'll talk more in a second about the differences in these two types of frictions. Well, in fact, let's do that now. So in terms of these two types, static is when sliding does not occur. Kinetic is when sliding does occur. And some other notes about these two types is static friction can actually change. I'm going to talk about that in a second. And the maximum static friction is greater than kinetic friction, and we'll see that on a graph in just a moment. Kinetic, however, does not change. It is a constant value. If I'm sliding, there is one value for kinetic friction, and we'll see that on our graph as well. So this time I'm going to pull it, but I'm also going to set the force sensor to collect data, and let's look at what graph we get for the force. So I see the force increases, then drops back down, and then is more or less a constant force for the rest of the time. So let me pause this. Go here. All right, so at this point, there are three sections of the graph I want to look at. I want to look at this section, A, that's rising, this section B, that drops back down, and then this more or less flat section here as C. Anything to the left or the right, I'll ignore that because that's when I actually wasn't pulling on the mass. Either I was before I was pulling or when I stopped. So section A, if we go back and watch, just rewind the video a little bit, section A occurred when I was pulling on the string, but the mass was not moving. So if I draw my free body diagram again, normal force, gravity, tension, friction. If this is not moving, I know that the tension should equal the friction. And what this force sensor is telling me is the tension force, since it's directly attached to the string. So when I'm looking at this graph, it's telling me the force of tension. But if I know that the force of tension and force of friction are the same, then this force of tension is also telling me the force of friction. So I'm getting a graph of what's happening in terms of friction. So let's look at this section A real quick. If this is telling me what's happening to the friction, that means as I pull harder and harder, the friction is increasing. Because no matter how hard I pull in this first section, the friction balances out that tension and the block does not move. So with static friction, if I'm pulling to the right with the tension, the friction just balances out that number, and that number can change. If I pull to the right with 2 newtons, then the force of friction is 2 newtons to balance that out. If I pull to the right with 5 newtons, the force of friction only has to be 5 newtons to balance that out. I can increase that to 7 newtons, then the force of friction would also be 7. Go all the way up here to almost 11 newtons, and the force of friction is 11 to balance that out. So with static friction, that number can change depending on what force is trying to get it to slide. And if it's not enough to break static friction, then friction will just equal out that number in the opposite direction. So at this point up here at the top, what's so special about that? Well, if I go back and watch the video, this is where the block starts sliding. So now it starts to slide, there's no more static friction, so my force changes. This section B, this is just it actually getting started and me trying to get it to a constant velocity. And in section C, I've achieved a constant velocity and I'm keeping the force more or less the same value. So now, even though the block is moving in part C, all the forces left, right, and up or down are still equal because I'm pulling it at as close to a constant speed as I can get it. If it's a constant speed, it is still in equilibrium. It's not speeding up or slowing down. So that means the tension force is still equal to the force of friction. So I see that in part C, when I have kinetic friction, this is when I have sliding, and remember A is when it's not sliding, so I know that's static. C is when I have kinetic friction. I see that kinetic friction force is a constant value, and it looks like it could be somewhere around 5.5 newtons, if I read my graph correctly. So we see that static can vary depending on what force is trying to get it to slide, but when it starts sliding, the kinetic force is a constant value. So now let's talk about how do I change the force of friction on an object. So now what we're going to do is we're going to take one of these masses off. So let's watch what happens when I take one of these masses off and do the same experiment again. So let's keep in mind that the maximum static friction here is somewhere around, well, not 11, but I'll say 10.5 newtons. And the kinetic friction here averages about to somewhere around a constant 5.5 newtons. So keep that in mind and watch how this graph changes when now I do the same thing again, but with less mass. So make the graph again. We see the same graph shape, but now we notice that the graph values are a lot less than what they were before. So now what's the max static friction? Well, the max static friction is somewhere around 6.5. And then if I look at this average value for the kinetic friction, that looks to be about 3 newtons. So why did this happen? Well, think about my free body diagram. I've got force of friction, force of tension, force of gravity, and normal force. By changing the mass, I actually made the normal force, or the gravity, the force of gravity less. Because force of gravity is mass times gravity, so if I decrease the mass, I decrease the force of gravity. What that also did was that decreased the normal force, because up has to equal down. This mass is not moving up or down, so those forces must be equal and opposite. So by decreasing the force of gravity, I decrease the normal force, And so something about this decrease made the friction force decrease as well. And we'll talk about exactly which one that was when we get to the formula in just a second. But right now I just want to get relationships. So decrease the force of gravity, I decrease the normal force, that decreased the force of friction. Let's do it one more time and see if we get the same result. So take more mass off, and we'll do this again. And I see the graph has the same shape, but now the values are even lower than what they were before. Okay, let's talk about some other factor that can affect friction. I have moved the block from the table to this piece of MDF that I've clamped to the table. So it's a different surface. I've kept the same mass as the original. So remember, in the original graph, my max static friction ended up being somewhere around 10.5 newtons. And then when I had my flat kinetic section, it was somewhere around 5.5. So let's see how it compares now that I've changed the surface the block is sliding on. Let's watch. So what I want to focus on here is the kinetic friction part. I probably should have done this graph again, because in reality both of these should increase. But let's focus on this flat kinetic friction part. The value here looks to be somewhere around an average of 8-ish newtons, which is greater than the 5.5 I got on the table. Now, why is that? Well, because if you were here in person, we would talk about how this MDF surface is rougher than the table surface. And so the force of friction also depends on smoother. What are we actually rubbing together? What are the two surfaces that are sliding against each other? So we talk about how do I change the normal force and how does that affect the force of friction, and then how does the surfaces themselves affect the force of friction as well. Which brings us to our friction formula. So the force of friction is dependent on the normal force, as we saw in our first example where I took the masses off. That changed the normal force, so it changed the force of friction. If you don't believe me, when we rub our hands together to keep them warm, if I only lightly press my hands together and I rub them, I don't feel much resistance. But the harder I press my hands together, that means the normal force between my hands is increasing, and the harder it is to rub them against each other because the force of friction has increased. Or if you try to rub your hand across a table, the harder you press down into the table, the more the table presses back against you, the harder it is to slide them against each other. So not only does it depend on the normal force, it also depends on this thing called the coefficient of friction. So what is this coefficient of friction? It basically is a number that describes how rough the two surfaces are that are sliding against each other. So the rougher the surfaces, the higher this coefficient is going to be. The smoother the surfaces, the lower the coefficient is going to be. So what would this look like in an actual problem? Let's do one, and let's actually figure out the coefficient of friction for both the table and for the piece of MDF. Let's take a look back at this graph we made for the complete total mass sliding against the table. Remind ourselves that we had an average kinetic friction of somewhere around 5.5 newtons. And so let's draw a free body diagram for what's happening when the block is actually sliding. So I've got the force of gravity down, the normal force up, the tension pulling to the right, and the force of friction pulling to the left. So there's actually two scenarios here. My maximum static friction was somewhere around 10.5 newtons, and when it was actually sliding, it was 5.5 newtons. The kinetic friction was. So let's look for two things. I want to know what is the coefficient of static friction and what is the coefficient of kinetic friction. And they are different because I have two different force values. So, first, let's look at coefficient of static friction. In this problem, first, I've drawn my free body diagram. The second step for solving a force problem is to use that diagram to write some equations. So up equals down, because this is equilibrium. Left equals right. And then, if there's any force I have a formula for, let's go ahead and substitute it. So for the force of gravity, we know force of gravity is mass times gravity. Mass times 9.8, mass times that acceleration of gravity. And I just gave you the friction formula as coefficient times normal force, and then there really is no equation for tension. So let's start plugging in numbers and see if we can solve. I'll go ahead and tell you that the mass of all three of these weights plus the block itself is 3.2 kilograms. So we can go ahead and find the normal force as 3.2 times 9.8, which is let's see if I can fit it here, 31.36 newtons. And then now that I have the normal force, well, let's look at my other equation. Well, I know normal force now is 31.36 newtons. I'm looking for the coefficient. And where am I going to get the tension force? Well, the graph is graphing the force in the sensor, which is the force in the string that's connected directly to the sensor. So for static friction, if this is not moving, that force maximum is 10.5 newtons. So if I solve for the coefficient of static friction, and I may go ahead and put an S on that to notate that it's static, it'd be 10.5 divided by 31.36, and we would get a coefficient of 0.33. Now, for a coefficient of friction, there is no units because I just divided force by force, which divides newtons by newtons, and those units divide out. So this is just a number describing how rough are the two surfaces that are trying to slide together. So that's the static friction force. Not force, static friction coefficient. What about the kinetic friction coefficient? What changes? Well, if I'm looking at kinetic, then let's start with step 3 again, because the equations don't change, because if I'm pulling at a constant velocity, then still left equals right, up equals down. I didn't change anything about the mass, so the normal force is still 31.36 newtons. So I'll go ahead and plug that in for normal force. But now with kinetic, the force of friction changes to be the tension force, which is the force of friction, changes to be 5.5 newtons. So it's less than what it was before. And we didn't talk about this earlier, but why does this make sense? If I'm trying to push a heavy object that's sliding on the floor, it is much harder to get that object to start to move than it is to keep that object moving. And we see that in this graph. If you are pushing on a table that's really, really heavy, to get it to start to move requires a pretty large amount of force, but you notice that you can ease up a little bit when you already have it moving. It's easier to keep moving than to start moving. And that's why we have static friction as being greater than kinetic friction, because it's always harder to start and break the static than it is to keep going with kinetic. But anyway, we have our coefficient here. It's going to be equal to the 5.5 newtons divided by 31.36, and I get the static friction, the kinetic friction coefficient, which I should put K for kinetic, is about 0.18. So the coefficient of static friction is always going to be greater than the coefficient of kinetic friction. Static is always greater than kinetic. But I will say your coefficient should never be close or even greater than 1. It should always be a decimal that's less than 1. If we get something greater than 1, what that probably means is we divided the wrong way or did some math wrong somewhere else. Let's do one more quick example, just to show that changing the surface changes the coefficient. And let's just focus on the kinetic part of this when it's actually sliding. So I've got the same free body diagram. I've got the same basic equations. Up equals down, left equals right. And I will take those, substitute mg in for force of gravity, coefficient times normal force for the force of tension, force of friction. And now if I take my normal force equation, I have still the 3 blocks, or the 3 masses on the block, so my mass is still 3.2, gravity is still 9.8. So the normal force, even though I change surfaces, the normal force is still the same because the weight is the same, or force of gravity is the same. So 31.36 newtons. Now if I take, that was my first equation, now if I take my second equation, that relates to the left and right forces, I've got coefficient times the 31.36 equals tension. So for the sliding part of this motion, what was the tension read in my graph? Well, it averaged somewhere around 8 newtons, like we said earlier. So if I solve for that coefficient, it's 8 divided by 31.36, and you get a coefficient of 0.26. And again, I should notate this is kinetic friction, so this is when it's actually sliding. So for the table, the coefficient between the block and the table was around 0.18 when it was sliding. For the MDF, this engineered wood piece, when the wood is sliding across that, you get a coefficient of around 0.26, which is greater. So changing the surface changed the coefficient, and the rougher surface has a higher coefficient. So I hope this was helpful and you understand somewhat about friction now. There will be some friction practice problems, and I will do an example. There'll be 5 of them. I'll do the first one, and you'll be responsible for the other 4.